Okay, so unfortunately, when I first recorded this thing, there was no sound, so I forgot to put on the mic. Uh-huh. Now I'll have to do it all of it. I mean, again, and yeah, let's just go with it. So this is like one of the easiest things in binomial theorem because it doesn't involve a lot of calculation. Anyway, so they are saying 1 plus x power n is equal to c0 plus c1x plus c2x squared and so on till cn x power n. So it's seriously just nc0 plus nc1, but they omitted that n, so it's assumed it's n. Prove that c1 plus 2c2 plus 3c3. So the first question, yeah, so all of these are just proof questions, so I will not be writing down the answers as I write down generally, right? So first you have to prove that C1 plus 2C2 plus 3C3 all the way till n Cn is equal to n times 2 power n minus 1. Come on, this is just so easy. All you gotta do is just differentiate this equation on both sides with respect to x because it's an identity, right? And from there, I mean, you can see how this quickly follows. This got n times 1 plus x power n minus 1. That's a differentiation of the left hand side. That's equal to, so C0, it becomes 0. Then C1 times x, that becomes C1. And then C2 x squared, that becomes 2C2. And you can see the pattern. So in the end, you'll get Cn x power n, which will become ncn x power n minus 1. It should be x over here, sorry. So 2C2x. And then so on till you eventually get n minus 1 right there. And yeah, now you'll notice that everything is perfect except you don't have this x in this expression. So just put x equal to 1, right? So then you can get rid of these values. So that's what we do generally when we want the sum of the coefficients. So you'll just get C1 plus 2C2 plus 3C3 and all the way till NCN. That will be equal to, so when you put 1 in there, you just get n times 2 power n minus 1, which is exactly what they want us to prove. So first is, I mean, it's just really easy. Second, C0 plus 2C1 plus 3C2. Yeah, so now you can see here it was n, now it's n plus 1, so it's just one more, right? What we can do is, I mean, write down the same equation but now multiply by x. So you will just have x times of 1 plus x power n. That will be equal to the summation of, so I'm just gonna write the summation, not giving the boundaries as well. So it will just be what? CR x power r plus 1, so n is assumed, and then just differentiate this thing, right? This will just be 1 plus x power n, so you differentiate x first, product rule, right? Remember the product rule. And then you got nx 1 plus x power n minus 1, and that will be equal to, so when you differentiate this whole series, just get summation of r plus 1 CR x power r, right? Brackets. Now just put x is equal to 1 in there and you will see what happens, right? When you put x equal to 1, you just get 2 power n plus n times 2 power n minus 1 is equal to summation of r plus 1 times CR. And this right hand thing is exactly what we're looking for, right? So when you put r equal to 0, it will be 1 C0, and then you got plus 2C 1, then 3C2, and so on. Eventually you will put n and you get n plus 1 Cn. Yes, and just put, I mean, okay, you already have this value, right? So now just recombine this. 2 power n minus 1 times n plus 2, right? So this can be done as 2 power n minus 1 times 2. That's fine. Yeah, easy. So second is also just really easy. Third is C0 plus 3C1 plus 5. Now this is slightly different. So you notice that it goes from 1 to then 3, then to 5, and so on. So there's a difference of 2 all the time, right? So we need to get that difference of 2 somehow. How am I going to do that? Well, I'm going to put x squared so that the powers, change by 2, not just 1. So 1 plus x squared power n, that will be summation of CR, in fact, just use R, and then x power 2r, right? Now, since they want C0, I mean, what we can do is just multiply this by x. So this will be, right, this thing. And then you can see what's going to happen, right? So for n, this term would be Cn x power 2n plus 1. So if you differentiate that term, you will just get 2n plus 1, 2n plus 1 times Cn, and then x power 2n. So when we will put x is equal to 1 to that term, you will just get 2n plus 1 and then Cn, right? exactly what we're looking for. So yeah, just differentiate this thing and put x equal to 1. So let's forget about this whole thing. Just find the answers. We'll be differentiating this and putting x equal to 1. So differentiate this first of all. It's going to be 1 plus x squared. And yeah, I mean, okay, let's first of all differentiate and then we'll put x equal to 1. But from the next question onwards, I'll just start putting in 1 directly, right? Plus, so keep that x, differentiate this thing. It's going to be nx, and then you got 1 plus x squared to the power n minus 1. But then the derivative of 2x, sorry, the derivative of x squared, which is just 2x, right? And then you put x equal to 1 in there. So you just get 2 power n plus n times of, well, that's 1. And that times 2 power n minus 1, and that times 2. So x is 1, right? That's going to be 2 power n times n plus 1, as we thought, right? That's what we want to prove. Okay, next. Next is 3c0 minus 8c1 plus 13c2 minus 18c3 up to n plus 1 terms. So that is equal to 0. So notice what's the pattern. So you have 3 and then you got 8. So there's a difference of 5, and then you got 13. There's a difference of 5, and that's alternating, right? So what I'll do is just figure out what 1 minus x power 5 is. Because difference of 5, and then you have alternating series, and that's why this thing. So that is of n will just be summation of CR, and then you got negative 1 power r, which is exactly what we see, right? When you put r equal to 0, this becomes 1, right? So that's why this alternating stuff. Then you got x power 5r. But what we are interested in having a 3 over there for the 0 term. I mean, for r equal to 0 term. So what I'll do is just put x cube, right? So that will just be 5r plus 3 now. And now when we will differentiate this thing and put x equal to 1, you will get exactly what you want. Perfect. Yeah, well, that should work. So just differentiate this thing. It's going to be 3x squared. And I told you, I'm going to put it directly at this point. So it's going to be 3x squared. It's going to be 3 in the end. So 3, and then you got, when you put 1 in there, oh yeah, all of that just goes away. Oh, huh. So 3 times 0, huh, that's gone. And then the derivative of this guy, that times x cube. That x cube doesn't matter because it's gonna put 1 in there anyway. The derivative of this thing will be like n times 1 minus x power 5 or n minus 1, whatever. And that times some other stuff, polynomial stuff, right? Thing is, 1 minus x power 5 to the power of n minus 1 still is there. And when you put 1 in there, that will also become 0. So it's just, I mean, the whole thing is just going to be 0 in the end. So yeah, this whole summation is just going to be 0, in fact. Okay, easy to prove. Next you have 2c0 plus 2 square c1 upon 2, and then 2 cube c2 upon 3. So notice over here you had multiplication by these these serial numbers or anything like some kind of AP. Right now you have division by the terms of an AP. So the way to do that is to integrate instead of having differentiated, right? Yeah. So right, first of all, just write down the whole thing. 1 plus x power n. What am I writing? It should be like this. 1 plus x power n. That's equal to summation of CR x power r. What we can do is just, integrate this guy. So we'll integrate from, let's just say 0 to x. Why 0? Because when you will put 0 in each of the terms after integration, you'll just get 0. So the minus term, that whole thing will be gone, right? And then this is not that hard to deal with when you put 0 there. Okay, so just integrate it. First of all, it's going to be 1 plus x power n plus 1 upon n plus 1, and it goes from 0 to some x, and that's equal to summation of CR upon so what we want is, for 1 you should have 2, for 2 you should have 3, for 0 you should have 1, and yeah, that just means you will need r plus 1, right? And that's exactly what we are getting, because when we integrate x power r, you just get r plus 1, the denominator, and then that times x power r plus 1 right there. Yes, and it will go from 0 to x as well. But then when you put 0 in the end, it's gonna be 0. Yeah, the whole series will be 0. So it's just like this directly. This though is not like that. You have to put 0 because it's not going to 0 directly. So this will be like 1 plus x power n plus 1 minus 1 upon n plus 1, right? So you put 0 in there, minus 1 and that's 1. Yeah. is equal to this whole summation, right? Now think about it. When you put r equal to 0, you just get c0 upon 1, and that times x power 1 or something. Over here you have an extra 2, and then when you put r equal to 1, you get c1 upon 2, but then x power 2, and then over here you have an extra 2 squared. So you get the idea, right? Just gonna put x is equal to 2 in there. It's gonna be 3 power n plus 1 minus 1 upon n plus 1. That's gonna be the thing. So it's gonna be summation of, I don't know, cr upon r plus 1, and you got 2 power r plus 1, right? That's exactly what this whole series is. Perfect. And that's what they wanted us to prove. So there we go. Fifth is easy. Okay, let's go to sixth now. So you got c0 minus c1 upon. So look, same thing. Let's go back to that. So you got this thing, this whole thing. Actually, no, I'll just go with this. Right? I mean, this is sufficient to do this. Right, so the same stuff. I mean, you got c1 upon 2, c2 upon 3 everywhere, but now you have an alternating negative, positive negative, right? So what you can put is just put x is equal to negative 1 right there. I mean, yeah, why not? Doing that, you will just get 0 power n plus 1, so it will be negative 1 upon n plus 1. That's going to be equal to summation of cr upon r plus 1, and then negative 1 power r plus 1, which is like, okay, negative 1 power r, but then that times negative 1. Why am I separating this negative 1? Because this. Yeah. So now you just get this summation. So let's just start putting r equal to 0. So you will put r equal to 0, you'll just get c0 upon 1, and that times negative 1 power 0, which is 1. Then from here it's going to be alternate positive negative. So negative, then you got c1 upon 2, and then positive c2 upon 3, so on. So you see the same series that we want, right? Exactly. And that's equal to 1 upon n plus 1. This is what they want us to prove. Okay, perfect. Okay, cool. Next you have 3 times of nc1 plus 7 times of nc2 plus 11 times of nc3 and so on. So what's the pattern over here? Start off at 3 going to... Oh, so you have a 1 over here, huh? Oh. So there's no c0. Huh. That's weird. I mean, okay, we can just put a c0 by ourselves. But okay, let's not do that. Let's save that for later. Right, what do we have here? So 3 nc1 plus 7 nc2 and so on. So you're gonna start from 3 and then go up by 4, then once again up by 4 whenever it goes up by 1. I mean the r value, right? So yeah, just gonna deal with 1 plus x power 4 and that times of x cube. So that's x power 4 power of n plus x cube. This will just be summation of cr x power 4 n plus 3 exactly. So yeah. Oh wait, but when you want 1, you should have 3, and this is not what we want, right? So in this particular case, when you will have 1, you will actually get 4 if you just have x power 4, and but then that times x power 3 doesn't make any sense, right? That would be x power 7. So instead we want something like, yeah, let's just slightly different. What we can do is just forget about this x power 3, and now think about it. You got 4, you want to go to 3. What do? Subtract by 1, subtract 1, right? Yes. So divide this whole thing by x. Now this will work, right? So when you put r is equal, should be r over here, not n. When you put r is equal to, let's say 1, you will get 4 minus 1, that's going to be 3. When you put r equal to 2, you will get 8 minus 1 is going to be 7, and so on. And that's what this series is. But you will also have that 0 term. So when you put 0, just get c0 times x power negative 1. So this will be equal to, so it's from r equal to 0 to whatever n in the end. Yeah. But we can write that as 1 upon x plus summation from r is equal to 1 to n of cr x power 4 r minus 1. And then what do? Just subtract this 1 upon x on both sides. It's going to be 1 plus x power 4, that to the power of n minus 1 upon x, and equal to whatever the series is. Now what we need to do is just differentiate and put x equal to 1, and we'll be done. Yes. So differentiating this thing, well, first of all, just differentiate this guy. So it's going to be negative 1 upon x squared, and then when you put 1 in the whole thing, this is going to be like, yeah, negative, and then you got 2 power n minus 1. So this is weird. 1 minus 2 power n. That's what you will get when you will do this thing. And then you gotta do that 1 upon x stays, and you want to do the derivative of this guy, right? So that 1 upon x just becomes 1 anyway when you put x equal to 1, so forget that. And just basically like take the derivative of this guy. That should be enough. So this is going to be n, and then 1 plus x power 4 power n minus 1, whatever. And then you got 4x x power 3, so that just becomes 4. So yeah, well, that should do it. Oh, okay, sorry. And that times of 2 power n minus 1, because you had that 1 plus x power 4 power n minus 1 actually. So that's why this thing. Oh, so you can write this as, I don't know, 2n, and then you got 2 power n or something. And we also just want 2 power n. So yeah, it's going to be 2 power n, and then you got 2n, and then minus 1, and then that thing plus 1, which is, yes, what we want. So there we go. Easy. So 7th done. Let's go to 8th. Prove that C0 plus C0 plus C1 plus C0 plus C1 plus C2, okay, so on, is going to be n times of 2 power n minus 1, where n is an even entity. Come on, I mean, this is like, you can just write in a beautiful format and you will see it actually works out very nicely. So this is like C0 plus C0 plus C1, and then C0 plus C1 plus C2. You see this pyramidal form or something, right? It's gonna keep on going, of course. But then you got these other n missing terms over here. You got this other n minus 1 missing terms over here. But wait a second. The last term, that's going to be C0 plus C1 plus C2 all the way till, well, C n minus 1. That's just exactly n terms. And wait, Cn minus 1 is C1. Cn minus 2 is C2. All the way till C0 is going to be Cn. So yeah, I mean, if you just duplicate this whole triangle and then put it upside down, you're going to get, well, basically n times of this C0, C1, all the way till Cn, not just Cn minus 1, Cn. And let's write that in a more understandable format, but the basic idea is just that. So this will be S is equal to C0 plus, like C0 plus C1 and whatever. And we can write it once again. So we'll start off at, C0 all the way till Cn minus 1 plus C0 all the way till Cn minus 2, and then so on. So each of these will have a pair, because, I mean, we're writing this one against another. It's going to work out, right? Yeah. It's just, I mean, n things over here, n brackets, and same n brackets, but written in the reverse order. And nothing about it. C0 can be written as Cn, and then all the way till Cn minus 1, which will be C1. So Cn plus Cn minus 1, so on till C0. That is going to be 2 power n. So 2s is equal to 2 power n, and then that plus, oh yeah, 2 power n once again. And then 2 power n once again, and so on. So how many of these? Each bracket will find its pair, and so each bracket from this series will find its pair and give us 2 power n. There are total n brackets, so this is going to be n times of 2 power n. And there we go, s is just n times 2 power n minus 1. Yes, so n is an even integer. I don't see why that should be the thing. Is it necessary for n to be an even integer? What if it's an odd integer? Does it not work? Okay, let's try it for an odd integer. Let's say, I don't know, 3. Try it till 3. So it's gonna be C0 plus C1, and then you got C0 plus C1 plus C2, and then plus C0 plus C1 plus C2 plus C3. Okay, you actually don't include C3 because the last would be n minus 1, and that's just going to be 2. Oh yeah, so no need for doing this thing. So like this whole thing, what is this going to be, huh? That's what we're looking for. So right, this is equal to S. You can write that once again, but upside down. So it's going to be C0 plus C1 plus C2. That can be written as C3 plus C2 plus C1, and that plus C0. I mean, come on, why would it only work for even integers? It's working for everything as I see it. Yes. Yeah. So for this case, I mean, S would just be 3 times of 2 power 2. So it should be 12. Let's see if really it is 12 or not. So you got 3 times of C0, which is just going to be, 3. And then you got 2 times of C1, which is going to be 6. and then you got 1c2, which is also just 3. So there we go, it's supposed to be 12, which is what we would expect. So yeah, this is true for any integer, not just an even integer. Okay, ninth. C0 plus C1 upon 2 plus C2 upon 3 all the way till Cn upon n plus 1 is equal to 2 power n plus 1. Oh, come on. Are you serious? Hey, haven't we already done this somewhere? No, we did this thing. I mean, it's pretty similar to that actually, right? So once again, same thing, just integrate this expression and then put x equal to 1. I mean, actually, no, when you integrate this, go from 0 to x and then put x equal to 1, right? And then you will arrive at this thing. So do I need to do it once again? I'll just do it. X plus 1 power n upon n plus 1, it goes from, well, in this case 0 to 1, yeah, I should say, is equal to what series we are looking for really, because like c0 times x goes from 0 to 1, c0, c1 upon 2x squared, 0 to 1, c1 upon 2, and so on, right? So this is going to be like 1 upon, oh, it's 2. 2 power n and then minus 1 and then upon n plus 1, right? Which, oh, it should be n plus 1 because integration, come on, increase the exponent and then divide. So that's why there's n plus 1, and exactly, that's what we're looking for. Let's go to 16 now. So you got c0 upon 1 and then c2 upon 3. Oh, that's different. So, usually, wait, actually no, it's very much the same thing. I mean, look at this, c2 upon 3, c0. Oh, only it's just the odd terms and not the even terms. That's what we are doing, huh? Right. So okay, we got the thing. So let's just go to x and not to 1 right away, and this will be equal to summation of cr upon r plus 1, and then you got x bar r. We only want the even coefficients, I mean the even r coefficients. So the way to do that is, first of all, just put 1 in here, right? I mean, okay, just actually write down the proper thing. Now, in fact, you know what, like this can go to I mean, we chose 0 to be the limit, but we could choose anything. So I mean, over here too as well, you have to put a limit over here as well. So let's just say -1 to 1. Why not? So when you do that, just get 2 power n plus 1 upon n plus 1 is equal to, now think about it, all of the even r values, well, those don't get cancelled. Now we don't want it to get cancelled. Okay, this is wrong. Okay, skip all of this, don't do it. The last equation was the best thing we could do, right? So this will be like x plus 1 power n plus 1 minus 1 upon n plus 1 is equal to this summation, right? This same thing. And then what we're going to do is just put x equal to 1, right? And then we'll put x equal to -1, and then we add and divide by 2. Why? You will see. So you just got to put n plus 1 minus 1 upon n plus 1 is equal to c0 upon 1 times, so when you put 1 in there, and then yeah, plus c1 upon 2 plus c2 upon 3 and so on. Then you will put -1, so you just get -1 upon n plus 1. That will be c0 upon 1 minus c1 upon 2 and then plus c2 upon 3. And now from here you can see the thing, right? Just add and divide by 2. That will give us c0 upon 1, c2 upon 3. Yeah, that's what we're looking for. So when you do that, you will just get 2 power n plus 1 minus 2 upon n plus 1 and that upon 2. So really just 2 power n minus 1 upon n plus 1. That's what we're looking for. Yes. Right? But you had to add and do this thing. So this shouldn't work. Why is this the way it is? Oh, sorry, it should be r plus 1, not just r. That's why it went wrong. So it should be starting off at negative and not positive. In that case, we have to subtract and divide by 2. Yeah, now I understand what went wrong. So when you subtract, you will just get 2 power n plus 1 upon n plus 1 and then divide by 2. So it's going to be 2 power n upon n plus 1. And that's why this expression. Now for the odd terms, so for the odd r terms, you would just add and divide by 2 and that would work, right? Yes. Do we have that odd R terms? Yeah. So look at this guy. So 12, C1 upon 2, and then directly C3 upon 4 and so on. So all of the odd R terms. So 12 we can sort out right away. Just add and divide by 2, which we saw it just gives us 2 power n minus 1 upon n plus 1, right? Yes. So 12 is done, and as well as yeah. So 10th is done, 12th is done. Let's go to 11 now. I mean, I would expect the its pair series to be over here as well, and that's why I looked for it. Not that I knew already. Okay, yeah, because it's been like 2 days since I did that recording, so I don't remember honestly. Right, let's go to 11th. C0 minus C1 upon 2 plus C2 upon 3 all the way till negative 1 power n times Cn upon n plus. So you got this alternating series, right? Uh, yeah, what we are looking for is like summation of negative 1 power r CR upon R plus 1. You can guess what's going to happen, right? Of course. So we'll just integrate this whole. Wait, have we not seen this before? Hey, we have seen this before. Where did it go? So what about? Look at this sixth and so look at sixth and look at 11. It's the same thing. Yeah, it's just repetition of the same thing. Fine. So then sixth and 11th same. That means 11 is also done. 13th. 2C0 plus. Okay, don't tell me this is also done already because it does look like that. So I think I've seen this somewhere, right? So 3 power n plus what? 1 minus. Yeah, but look at this guy. 2C0 plus 2 squared. Ah, come on. Why? So this is the same thing. So 5th and 13th, these match up exactly pair by pair. Oh wow. So there we go. 13 is also done, even though we did technically nothing. Okay, 14. 5 6, so it's different. I have not seen this before, right? Throughout this should be new. I say it's new, but really it's just the same thing as before, right? So you're gonna start off at 5, and then it's a difference of 4. So if this series would continue till C0 as well, you would have 1 C0, I guess. Yes. Yeah, and then oh yeah, so what you want to do is just figure out x times 1 plus x power 4 to the power of n. That would be summation of CR x power 4r plus 1. And when you will differentiate this thing, so it goes from 0 to n, of course. It's not the complete series. I mean, okay, it's actually more than the complete series. So you need to get rid of that 0 term. Right. So when you will differentiate, you get 4r plus 1 CR x power 4r. You will put x equal to 1 in there, and then you just get 4r plus 1 CR. And so when you put r equal to 0 in there, you just get 1 CR, sorry, 1 C0, and then with r equal to 1, you'll get 5 C1, and then yeah, so on. So that's what we're looking for, right? So just gonna differentiate it. But before that, we can get rid of this 0 term by separating it from the summation. So it's gonna be plus C0, and then you got x power 1. Yes. So this is like x times 1 plus x power 4 to the power of n minus 1. That is this summation. So summation from 1 to n of CR x power 4r plus 1. And then now we can just differentiate this. So just put x and then put 1 as well. So differentiate x and then put 1 in there. This is going to be 2 power n minus 1. Okay. Plus, so don't do this, just put 1 in there. That's gone anyway. And then differentiate this guy. So that 1 is going to be gone, right? It's just going to be n times 2 power n minus 1, and that times of 4x cubed. So just 4 because x cubed is 1. Yes. So that will just be 2 power n minus 1 plus n times of, but I should say 2n times 2 power n because I want to combine some stuff. So 2 power n, and then you got 2n plus 1, and that minus 1. Is that the answer? Where is it? What question was I doing? 14th, right? Oh yeah, it's the same thing. Cool. So 14th is done. Go to 15th. C0 upon 2 plus C1 upon 3. Right. So, oh, I mean, normally we have C0 upon 1, C1 upon 2, but now you got an extra 1 over here. Yeah. Well, you know how to do it. I mean, just multiply the whole thing by x. This will be x times of 1 plus x power n. Yeah, but that's going to be summation of cr x power r plus 1. And now you can just integrate this thing and go from, well, 0 to 1 directly. So that, yes. Oh, okay. In the next 16, you also want to go to negative 1. So we'll just go from 0 to x instead. Right. So from 0 to x, you just get the whole series we are looking for. And then you can put 1 or minus 1 in there as you like. And you just need to integrate this. That's right. That's what we want to do. So, okay, we can write x as x plus 1 and that minus 1. So minus 1 plus this guy. That will give us 1 plus x power n plus 1 and then minus of 1 plus x power n. And then integrating this is a piece of cake. So this will just be 1 plus x power n plus 2 upon n plus 1 minus 1 plus x power n plus 1 upon n plus 1. And it goes from, well, this whole thing actually goes from 0 to x. So it really just becomes 1 plus x to the power of n plus 2 minus 1 upon n plus 1. And then minus of 1 plus x power n plus 1 minus 1 upon n plus 1. So now we gotta put x equal to 1 to get 15th term, and that will just give us 2 power n plus 2, which it's supposed to be n plus 2 right there, not, yeah, that's how it should be. And you wanna, oh, so you will have to cross multiply anyway. That's not good. Fine, so if you wanna cross multiply anyway, we'll just do it direct. We will take 2 power n plus 1 common. You will have 2 times, well, when you will cross multiply to get n plus 1, so it's going to be 2n plus 2. And then minus, so n plus 2, so it's going to be minus n minus 2. And then the other minus and minus 1, it's not affected by this exponent. You just got n plus 1 times this guy, and then minus of 1 is going to be plus, so n plus 2 times of that, which is going to be 1, because n plus 2 minus n plus 1 is just 1, right? 1, 0. And then that upon the multiplication, so it's got n plus 2 times n plus 1. I mean, of course, these are going to be co-prime. Huh. So that's the only way you could do this. No simplification. I mean, even if you put n as an actual value, these will be co-prime, right? Number theory. Anyway, that's the thing. Now, for simplify this, it's got n over here. And then, oh, this cancels. But, this is weird. So you got n times of 2 power n plus 1, and that plus 1, and that upon this whole product. Right, that's what we're looking for. So perfect. And then you just got this positive negative thing. So you had x power r plus 1 and that times cr, and that upon r plus 1 as your cr x power r plus 2 upon r plus 2. That would be the thing after integration, right? So when you will put negative 1 and also r equal to 0, you will get the first term to be positive, right? Because r plus 2, so 0 plus 2, x power 2. So it's gonna start at positive anyway, so you don't have to worry about that multiplying by negative and everything. So just put x is equal to negative 1 in here, and let's see what we get. That will be your final answer. So this will be like minus n, it's minus 1 upon n plus 2, and then you got plus 1 upon n plus 1, because I mean these will get cancelled. 0, 0, yes. This will be 1 upon n plus 1 times n plus 2, right? So that, do the whole math, n plus 2 minus n plus 1, 1. It's gonna be this thing. So 16th done as well. This is it. Okay. See you guys in the next video.